how, right? So that's the outline of the talk. So I'll give you a brief introduction to the Hubbard chains. I know Eduardo Miranda already did most of the job here, so I will be quick in this part. Then I will try to give you some insights of how entanglement can be used to detect quantum phase transition or to mark quantum phase transition in the systems. And then the interplay between disorder, interaction, and entanglement. And finally, discuss a little bit how we can associate entanglement with work extraction in this kind of systems. And as Andrade said, he had a bonus topic in the end. So if I have time, I also brought some bonus topic for you guys. So as Eduardo said, we have this Hubbard model, which in the one-dimensional case means I would have some sites with a certain particle distribution there. And for the single band model, which is the simplest Hubbard model, that means I can allow for only 2 particles in a given site. And we map this in this Hamiltonian, which accounts for the mobility of the electrons within the chain. And in the simplest case, we just consider mobility between neighbor sites. That's the T, the Hoping term. And we also consider the interaction, on-site interaction. Of course, you can plug in extra terms, long-range interactions, but we here will use only the on-site interaction for the chains. And in principle, you can add some extra potential, for example, to describe your disordered system. So the nice thing of this model, for example, if you just use the U interaction as a positive interaction or attractive interaction, you can map different physics, several phenomena there, at least qualitatively. So for example, for U larger than 0, we know that we have a metal in most of the regimes for the density distribution around the chain. And at n equal to 1, we reach the insulator, the Mott insulator phase. Now, if you plug in attractive interactions, so you can simulate with this Hubbard model a superfluidity phenomena. So it could be the conventional one, the BCS superfluidity, in case where we don't have any imbalance between the spin populations. So that's dp, the polarization within the chain. And you can also see some other phase if you add this extra magnetization, this internal magnetization produced by an imbalance of the spin populations, right? So the so-called FFLO, superfluidity, and so on. And no problem. Now, if we move to this extra term, well, of course, you can do many things with this V. But for give you some examples, you could plug in this localized impurities in a random distribution within the chain and try to give some answers for Anderson localization. You could also plug in some harmonic trap, trying to simulating codatom systems. And I also citing here the super lattice one, which could be then a modulation, a periodic modulation of this external V, then producing some interface in the chain. Okay, so and why the Hubbard model is so important, right? And well, that is essentially even in this simplest model, in the simplest version, you can describe at least qualitatively most of those phenomena that I've mentioned before. But actually, if you plug in extra terms or if you go to some specific limits, for example, including more bands for each site or going to some interaction regimes, you map the model to many other models. So that's why, together with the Heisenberg model, the Hubbard model are one of the most paradigmatic models within condensed matter physics and material science, and at some point also in chemistry. Okay, and here just a relation of how we can then map physical systems by plugging different structures or additions in the Hubbard model, right? Now, So how we are using the Hubbard model to explore entanglement within disordered chains. We are defining a very particular type of disorder. As Eduardo mentioned, has many other possibilities to define or to simulate the disorder within the chain. In our case, it's the binary one that is just this point-like disorder. So what does it mean? So we have the one-dimensional Hubbard model, Hubbard chain here. And then I have some specific sites within a certain concentration that I will define in a moment, with a certain impurity V there, right? So these blue dots means no V, and the red, for examples, are the V sites. And in our case, we are doing this for a certain number of impurities, and we are keeping fixed, let me just, keeping fixed the intensity of these impurities. Instead, what we are varying is the concentration defined like that within the chain, right? And we also, and it's important to notice that we do a certain number of samples where these positions where the impurities lie within the chain are random, and then we take average on these many realizations. So just to give you an example, I'm going too fast with this. Just to give you an example of how one of our quantities goes with this number of samples we take into account for getting the average. I will talk in a moment what is this entanglement here in particular, but the most important quantity that I will show to you in the entire talk goes like that with the number of samples that we take this average, the number of realizations for a given particular distribution with a fixed concentration and a fixed V, right? So we see that if you take care here for the scale, it's quite small with entanglement measures, and I would say beyond 20 samples is already a quite good result, but actually we always take 100. Okay. Now, Eduardo also said, okay, it is the 1D Hubbard model is one of the cases where we have exact data for it. And we do have exact solution, that is the Bethe-Ansatz solution for the 1D Hubbard model. But the problem is that this exact solution is only for the homogeneous chain. So that means no disorder at all. So, of course, also no finite size effects and so on. So when all the sites are completely equivalent, then we have the exact solution. But of course, we are interested in more realistic systems somehow. So just to point out some, those are the ones I mentioned before. So the point-like disorder is the main one we will discuss. This will be the bonus topic, if I have the time to enter on the topological stuff. And well, this is just the super lattice structure that I mentioned. So in all this case, I definitely have a particular dependence on the specific site. So all the distribution here will clearly be inhomogeneous. And that means I can do, of course, exact diagonalization, but then I would be limited to the size of this chain. What could be very complicated for exploring, for example, disorder, since how random can you really do something with only 20 sites? It's a bit complicated. Then you can go further with almost exact methods like DMRG, but that has a high computational cost. Remember, I have to do 100 samples for each set of points. And we have the approximated methods. There are several of them, but we use this dense functional approximated theory, dense functional theory. So, and with that, it's definitely approximated. I will give you an idea of how good is this approximation, but definitely it has a much lower cost for the calculations. So, considering it's a school, I've used some, let me get my water here. I've prepared just 2 slides to give you a brief idea of the DFT calculations. that we could think first that's essentially based on this first theorem, Hohenberg-Kohn theorem, that establishes a mapping, a unique relationship between the wave function and the particle density N of R, right? So within this mapping, that means all the observables that in principle you calculate like this are also a functional of this density. So in principle, given that there is a unique relation between wave function and density, particle density, if you have the particle density, in principle, you would be able to extract any observable or write down the observable as a function of this density. Of course, from this point of view, from the numerical point of view, it is much simpler because you would switch from a much more complex quantity, which depends on 3n, so increase with the number of particles there exponentially, while for the density, it would be a much simpler quantity. And it's very hard to look from here. Yes, so in principle, we could obtain like that. But the point is that only with the Hohenberg-Kohn theorem, we have no idea of how to obtain this other magic quantity that is the density, the particle density. So in one hand, we know that we've had this density, we could have any observable, but we have no idea how to obtain this thing only from this. So then, of course, just a few years later, or one year later, there was a scheme that was proposed to solve this first problem, that is to obtain this density, the particle density of an interacting system. And the idea is quite simple. The idea is essentially to map an interacting system that is quite complicated. You have this Hartree potential, the exchange correlation energy, and the external one. So all the interaction effects definitely are there, trying to map this interacting system to a non-interacting one. So of course, this non-interacting system is a fictitious auxiliary system that would give you some hints on the interactive one. And how does it work? So essentially, you constructed this fictitious one with a certain effective potential, Vf here, and you force that this minimization of the energy with respect to the density reproduce this guy here. So by doing this, definitely this effective potential must be written like that, and then in principle, you end up with a simple non-interacting system, which you could solve by single particle Schrödinger equation, and then from there, extract information of the interacting system. The problem is that you end up with a self-consistent cycle here, because this depends on the density. So how we manage this? So first we give some input for the density here, a tentative density, then we solve the Schrödinger equation. We calculated with these wave functions here, that is the constant orbitals, the non-interacting wave functions, and we calculate the new density and restart again this cycle. So that's how we do that, up to a certain conversions criteria that you decide for this and for the energy, right? So that's the main idea, but there is something here that is hidden in these equations, that is the exchange correlation potential. This guy has most of the interactions, the correlations between these many particles, apart from the heart, who was separated here, this heart contribution. And typically, we don't know this expression in general, right? So here, up to here, if you manage to find out this functional, this exchange correlation potential, you would be able to do exact calculation. So up to here, DFT is considered exact. But at this point, as we don't have this expression in general, we have to adapt to some approximations. And there are many of them already. Of course, there is not only for the Hubbard, but for any electronic system. But I will describe only the one that I use in those entanglement calculations, which is actually the simplest approximation that you can propose. So the idea is the local density approximation, right? And the idea is the following. So you have an inhomogeneous system, and here is just a random distribution of these particles at this space, okay? And within a local density approximation, what we do is, first we have to know the information that I want to know, let's say a certain observable wall. I need to know this for the homogeneous case. So if I have the information for the homogeneous, what would be just a line here in this map, then I can do a local density approximation. How we do that? Well, we simply, it's here. So we simply use point by point. We take that homogeneous quantity, that homogeneous function that we have for that particular observable, and we replace in that formula the density by the local one, right? So essentially, when we do this, if you have this input here, then you have a local approximation for that particular property too, okay? So of course, that becomes better if this inhomogeneity here found is smooth. And in the limit that is a constant, you recover the exact data as it should be. But it might be a very good approximation in case where you have also a very good homogeneous functional for that property you are interested on. So in particular for the exchange correlation energy of the one-dimensional Hubbard model, we do have the exact data from beta-ansatz solution. So this means LDA for this case will work pretty well because you start with an exact input here for the homogeneous system. Then the approximation is only on this spatial distribution of the densities, right? So, so we have the exact numerical solutions, but we also have some other possibilities. For example, you could use analytical parametrizations for the 1D Hubbard model. We do have at least 2 of them. You could also use some machine learning models, which is numerical, or more recently, we have developed a new one that is a hybrid parameterization. So anyway, so we found a way to solve, sorry, I thought it was a question, to solve the 1D Hubbard model in the inhomogeneous case. And just to give you an idea of how good this approximation can be, I've brought some of the results here. So here is just for the total energy.
Vivian,
sorry.
Just a quick question.
Sure.
In principle, you can solve DFT for the homogeneous case and then use this solution into your local density approximation, right?
It's not DFT in this first part that you mentioned. It's not DFT. So let me just come back here. So in principle, what we do, it's already enough. So what we do is, if you have some information here for the property you want, this part is not a DFT, right?
Oh, okay.
So you have to know, let's say you want to calculate the property A in an inhomogeneous chain. So you can do DFT for finding the heterogeneous density, how the densities are distributed. But for that particular property, you have to know the density
the property
functional.
as a function of the DFT will give the N, right? So,
yes,
okay, yeah.
yes. Now I think
I got
it's
it,
correct.
Got it. Yeah, thank you.
Welcome. And then, so that's just to give some taste of how this approach goes. That is the energy deviation as a function of the system size, so the length of the chain, the 1D chain, with no impurities or disorder or external potential there. So it's just finite size effects. And as it should be, so we see that, of course, for strongly interacting system, this LDA approach goes worse. but it decreased quite okay, depending on the number of the average density of the chain with this size for the energy, right? We also have here some for the entanglement quantity that I will talk in a moment as a function of the harmonic trap. So here is also comparing to, in all the cases, the points are DMRG results. So, and here is for particular transitions, we saw there in that confined case, and we see pretty well also. Actually, for this quantity that we will use, that is a particular type of entanglement, we see that the deviation is much smaller in comparison to the energy. And I will show you in a moment why, the reason for that.
I have a question. You are comparing the energy deviation from something that you say that exact and the one that you are comparing with DFT.
Yes.
What is the one that you say that is exact?
It is the DMRG calculation. So it's numerically exact or almost exact.
Okay,
yeah, that's the one for these finite chains. And here are cases for disordered systems that most of the talk will be on this specific case where we have no interaction or with disorder and with interaction. So we see peculiar trends in this entanglement property. And the red points are DMRG data, while the blue curve is the DFT. So most of the case, we can trust on entanglement. That is the main message for this thing, because we are using very good functionals within the LDA approach. Okay? So now let's talk about what kind of entanglement we are actually plugging there in those graphics. So to begin with, let's remember, essentially, if you have just two subsystems A and B, and they share entanglement between them. That means if you perform a measurement in one of the subsystems, let's say A, you affect immediately the state of the other part, the state of B. That's the general definition. And in principle, actually, this A and B can be almost anything. So it could be two different particles, it could be two molecules, it could be even spatial regions of a given system, and it could even be degrees of freedom of a same particle, of the single particle. Okay? So A and B is very important to define first before ask what kind of entanglement you actually have there. Okay? So, but one thing that's very important for us to know and to use this as a marker for quantum phase transitions is the following. Entanglement is not a property that is present or absent only. Actually, you can quantify different degrees of entanglement. That depends on how much information you could extract from B by applying measures on A. So these quantifiers give you a certain degree of entanglement. And that will be very important for us here. Now, apart from the degree, it's also something that we expect that when you go, for a given parameter, if you cross to a phase, a different phase, so if you cross from one phase to the other, it's reasonable to expect that entanglement there will show some signature. And then, so that is essentially how we use this entanglement to try to say something about different phase. And I will focus particularly on this one, from superfluid to insulator at t equal to 0, most of the results. But the point is that entanglement can be used then as a sound. Okay, so since 2017, we have been working on connecting entanglement with several possible quantum phase transitions in different systems and so on. Of course, I won't bring all of these things, but some of them. And I also would like to say that there are, most of the works here are actually with some of our collaborators. So now, the first type of entanglement here that I want to discuss is what is called average single-site entanglement. What is this? Essentially, within that chain, I specify a single site A and calculate how is the entanglement between this piece, this site, and the rest. So that means the entanglement between the possible states of that single site, which is just 4 possible states. For a single site, I can have 1 occupation with spin up, 1 occupation with spin down, no occupation, or a double occupied site. So how these 4 possible states of a single site is entangled to the remaining sites of the chain is what this single site entanglement measure quantifies. But of course, I can do this for this first site, and that would give a very different result if I use the second or the third and so on. So depending on where this site is chosen, you can find a different result. So the idea here is that you could then take an average of all the possible sites and have some average information about the single site entanglement for a particular system, okay? And why this quantify entanglement? Because when we divide it like that, we can write here. We can write both of these entropies that are known as good measures for entanglement, for bipartite entanglement in a pure state. That is exactly what we have in the ground state of the Hubbard model. So in this case, in particular, these 2 quantities are well-defined to quantify an entanglement. This one is the proper measure. This here can be useful in some regimes, but I recommend this paper here where we show that it's not always the case. So I would keep the von Neumann entropy one, okay? But actually, these are quantities that you can obtain by simply having the states of that single site, right? So these are the probabilities on the occupation base, which is related to these other quantities, that is just the total density, the average density, sorry, the average magnetization, and the ground state energy of your system. Well, with that said, that's important to notice that these entanglement quantities are actually density functionals. You can write down the expression in terms of the density, spin and charge density. So that means we can do DFT to calculate this thing, and that's what we do. And also, there was this piece here. So we do an average entanglement, that is just the arithmetic average. You could do the typical entanglement, which is the geometric average of this single site entanglement. And if I have time, I will show you some results of this entanglement profile. That is just the information within the chain without taking the average, any average. So it's really looking a picture of how entanglement is distributed along the chain. Okay, so let's start to see what entanglement looks like when we have some interesting phases there. And we start with the repulsive interaction U, is still without disorder, so I just vary the density, right? So here, that quantity is the average single site von Neumann entropy obtained with, in this case, with DFT, within LDA, and so on. I hope you could follow more or less the steps. But the idea here is that then I'm looking on that average quantity as a function of density for several interaction strengths. So we see that starting from U equal to 0, the maximum entanglement occurs actually when we have the sites maximally filled with n equal to 1, all right? And that is because those 4 probabilities are essentially 1/4 in this case. When U equal to 0, none of the states are favorable, so you have the better distribution among that states of the site. Now, if you turn on the interaction, it's hard to see here, but in all cases, for any interaction, actually, it starts to appear this local minima precisely at n equal to 1. That means that's the way this type of entanglement is pointing out the Mott insulator phase here at n equal to 1. And there are also some interesting features. For example, we see that for a certain regime of densities, there is no effect on vary interaction. That is because the density is too slow for make some difference from the entanglement point of view by increasing their interaction. And okay, we have the minima there. But another thing that's very important is that even when we do this interaction going to infinite, it never vanishes the entanglement. So we never totally localize that state. A single site is pinking in a localized state. And the reason is because despite the fact that we are freezing the charge degrees of freedom, I think it's my bottle. We are freezing the charge degrees of freedom, but not the spin degrees of freedom, okay? So, and then, okay, I think it was there, right? So that's the reason, simply. All right. Now, if now we do the opposite, so we turn off the interaction and just plug in disorder on that specific type that I showed you before, what this entanglement, this average, normal average entanglement gives to us, again, as a function of the density, now for several disorder strengths. So, okay, this case here is the same curve that I had in the graphic before. So maximum entanglement here at n equal to 1. But now turning on the disorder strength for a given particular concentration, and that was for 50% in this particular case here. So just increasing the intensity of disorder, what we see, first, it's nice to see that for any interaction, the curve immediately separates from the clean case. That means for any density, the presence of the disorder, even the smallest case, is enough to decrease at some amount the entanglement, right? Different from the MOT case. But actually, we see that it does not change much when you have that in the same region of a small interaction. Now, here at the center, it starts to appear, depending on the strength of the disorder intensity, we can see a minima, a local minima here. And in this case, well, we found out what is the precisely critical density where it appears. It's proportional to C. C is the concentration of impurities in your chain. But the point is that the minimum goes to 0 in contrast to what we have seen with the interaction, right? So you could imagine that from the single site point of view, that means you have a full localized state. Okay, sorry, it's passing too fast in the final pieces of the slides. Now, that was results. These were results for normal average, for arithmetic average of the single site entanglement. Now, this work by Eduardo and collaborators, they have shown that in principle, these average quantities are not well, it's not the best choice for describing disorder systems. It would be better than to use typical quantities in general, although it was in a different system, a different model, right? So then the idea was, let's then do the typical case for us too. And that's precisely what we have here. So this one was for the average case, just with less V points here. And that is the typical average of that single site entropy. So the typical quantity, the typical entanglement, or the geometric average of that thing for the same values with no interaction yet, with the same 50% of concentration of impurities, 100 samples, and so on. And we clearly see that that feature that appeared before for small densities disappear actually in the typical case, meaning that there is, well, the entanglement goes to 0 for this regime, while the average was not seeing this. So definitely this typical, at least for the small density regime, this typical quantity is definitely more sensitive than the average one. But for, depending on the strength of the disorder, for example, this curve here, that is quite bad to see, but I think it's this one. Yes, so that is for small v, it's v equal to 1. We don't see much of a difference in this case. So it seems in the regimes where they are similar, actually it seems that the system does not localize. It's not a problem of an average that is not seeing well the system. And if it's true, this is a work in progress, but if it's true, then this means that minimum intensity of the disorder necessary to reach that localization would be finite, would exist, a minimum disorder, right? So then if you are interested on this particular comparison between average and typical, I invite you to visit Silvio Quintino's poster, where he did many other tests with these two particular measures. Now, with this, I would like to go to the system where we have attractive interactions and disorder, okay? Well, within this case, essentially, as soon as we turn on the interaction, we turn on the disorder there, independently on the concentration of impurities that I actually have in the chain, we see an abrupt drop in the entanglement value. So that's the average one, and we see that it drops a lot for very small V's, right? So almost 50% in all the concentration case here for a given interaction and density. So this thing here suggests that in the attractive regime, so that's the case here, there is no minima. There's no minimum of the disorder intensity required to reach localization. Okay. Also, the fact that it saturates quite fast, as we increase further this disorder strength, we see the saturation. That is one of the typical signatures from the entanglement point of view. When you saturate this beyond a certain parameter, that means you are already in a maximum localized from the entanglement point of view. Okay? So in this sense, then in this particular case, as this model is with the attractive interaction U, that means your BCS pairs are very strongly coupled on that impurity sites, since this is attractive, right? So forming these strongly coupled dimers. Now, when we look at now this thing for a fixed V's and vary the concentration, we actually see a transition, a first order transition in the particular concentration that is related to the particle density there, right? But it's still necessary certain, in this case, it's important to have some minimum disorder strength to generate, to reach that fully localized state with zero entanglement. All right. So now, one of the questions we made was related to, could we use somehow this information of this entanglement to connect with quantities as, for example, work? Could we perhaps find the best regimes where we could extract more works of a given 1D system? So, and then to explore this, what we do, we essentially did some sudden quench, specifically in the disorder, attractive Hubbard model. And we explored two different types of quenching. That is, one of them is by keeping the concentration fixed. So for example, this is one site with a given impurity. So it's always one site, only one, but it's randomly placed and so on. But we also define a different intensity for the final state. So that would be the quench in the strength V. And we also do the quench in the concentration. So in this case here, V is fixed, Vf is equal to V0, but the number of impurities that you have is being varied. And we do this and analyze then how is the work, trying to connect with the entanglement that we saw before for this particular system. So first, in the quench in V, we see that most of the curves have this negative work. So for work extraction, it's not so effective. There is just 2 cases where it's positive, but it's still in very specific positions. While for the second sort, it's missing. Oh no, that's the entanglement. That's right. So if I compare for this quench and how the work behaves with the concentration, it has almost nothing to do with the picture that we have before from the entanglement point of view. So there is no clear relation here between the quantities. But when we do the other type of quench, so within the concentration, and well, of course, it's normalized and so on to plug in together, but it clearly shows a maximum positive work, so a maximum extraction of work here, precisely where the entanglement in the ground state is minimum. So this connection between entanglement and work, so the relation is there, and it could be useful for something, for extraction, work extraction, and so on in this type of systems, right? So now one of the points that we would like to address here better is not the sudden quench, but to see over time the evolution and the adiabaticity within these protocols and so on. So here is the conclusion of this part, and I think then I probably will have the time for the bonus thing, right? So from the quench point of view, we see that the quench in C is much more sensitive, more effective, sorry, in producing work than the quench in the disorder strength. We could relate it, at least this information that we know when we have lowest entanglement, we have the maximum extraction of work, at least in one of this particular type of quenching. That is what is written here, okay? So as I didn't know if I would have the time here, I plug in some things extra here to show to you. First is the following. It's always some question, okay, you are calculating work that in principle could be useful somehow for quantum batteries and so on, but with a quantity that is this single site entanglement, average, and blah, 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 which is not exactly measurable in the lab, right? So how can you really use the relation that you just got from there? So, of course, it's an important question, and there are many issues, effort on trying to relate the entanglement to measurable quantities. And one of them that I would like to emphasize is the connection with the magnetic susceptibility. So, in this case here is for the 1D at t equal to 0, so exactly at that regime we were before. So here for a certain small value of interaction, we find not only a linear behavior between these two quantities, the entanglement and the magnetic susceptibility, in the opposite, right? But, we not only find that it's linear, what is quite simple, but also we could find the way they are connected with the other parameters of your system in terms of density and interaction, in a sense that we could lie in all the points in a single universal line for this relationship between entanglement and magnetic susceptibility. Of course, it's t equal to 0, 1D, so quite limited yet, but more recently, we also did similar stuff for 2D case, for 2D chains in different geometries and finite temperature, and we still see some regimes where here the points are varying U, the interaction exactly as here. So where we see some regimes where this linear relationship is still there between that quantity that we don't know how to measure and some measurable quantity. So it's no way to give a motivation why we still so interested on this kind of thing. So in principle, there are, we have some advances on how to experimentally probe this entanglement quantity. Right, so before, thank you, that's my last topic. I just would like to give you some impressions of how we also use entanglement profile instead only on the average. So in this case here, there is no disorder. I still have the attractive interaction regime. And instead of disorder, we plug in the harmonic trap. Right? So you have this parabolic potential here in the Hamiltonian. We have seen already this average single site, but now we could also use other quantities. And in the very end, I'll show you how they are connected. But you could, for example, use the entanglement average, but only within the trap center where actually the particles lie. So because the intensity of the potential here, you have several sites in the borders that are simply empty. So they are concentrated here, so you could do this average in this effective region. What is this here? We can also divide the system A and B and use the same formula for the von Neumann entropy in different ways. So for example, we could share, split here, sorry, the chain in the half. That would be this L/2 entanglement measure, right? And the one that I will emphasize the most here is this entanglement profile. So without taking any average, just look at the picture of how entanglement is distributed along the chain. So, and for comparison, in this particular work, we also use this pair correlation here, that is the superconducting order parameter, defined like that. Okay. So then what we do here, let me put something. So first, let's take a brief look of how that confinement affects the system. So starting here from k equal to 0, where here we have many sites, so essentially we have a homogeneous distribution of the particles. When we increase the curvature of that parabolic potential, essentially we force the particles to go to the trap center. And when we do that, there is a point, well, we started with a BCS superfluid, but there is a point where these center sites are doubly occupied. And in this moment, we have an insulator phase. We are calling this a band-like insulator just because we really have the full filling for those sites, okay? So there is this transition from a superfluid to insulator here, but there's something happening in between on these rings of the harmonic potential, right? So this is the conclusion. Okay, you also decrease the effective region where the particles lie, depending on the K, and so on. Now, it can also be seen, so you could conclude that K drives the transition from here to there, but we are not really giving some more details on this respect. Well, this physics can be mimicked also if you fix K and simply plug in more particles there. The physics will be pretty much the same. So essentially, for a fixed curvature, if you fill in the particles within that system, you see that at some point, you have the insulator phase there. And there are also some features here, perhaps smoother, but also some features here. So in this work, what we did is, okay, how that the entanglement profile probe this transition from a superfluid to an insulator phase. And so here are the results for varying K and for varying the density. And we see first that they are more or less the same physics is there. But one thing that is very important to notice is that we start with a highly entangled system, which is the black curve. And when we increase the K, either K or the particle density, we see a decrease on entanglement, in particular at the center of the trap, right? and until finally reach that insulator phase. So now our aim is, first of all, try to identify better what is this regime here that is not really a superfluid, not at all an insulator. We are calling this a metal, and I'll show you in the next slide how the gap behaves within this regime, proving that it's actually a metal. But one thing, two things I would like to call the attention to this graphic is first, the fact that I'm changing K and I'm changing the particle density, and none of the Ks has changed. Neither of them was able to change the maximum value of entanglement observed on these different systems. So you see that there is a robust thing happening in these border sites that keep the entanglement constant and almost maximum there. And the second thing I'd like to call the attention is that the red curve are the pairing correlation, so the superconducting order parameter, that's semi-quantitatively the same as the single site entanglement, showing that the thing here is actually a superfluid. So you will start with this value of pairing correlation, and it's essentially there in the very end. So the rings, where we don't know exactly what was happening, keeps as a superfluid with an insulator inside. And let me just put this here. And well, we could calculate the gap as a function of one of those parameters, and we see that the gap tends to 0 precisely on that particular region, where entanglement also decreased, but is not vanished yet. And after that, when we reach the insulator, the gap increased further again, so showing confirming the insulator regime. And when we look in more details on these particular probabilities, average probabilities of those border sites where the peculiar constant entanglement appeared, we see a nice symmetry there. So locally, these two probabilities are always comparable, quite equal, quite similar. It should be approximated here, but they are essentially the same within these rings, resulting in this symmetry locally between particle and hole, right? So with this, we are then claiming, it's not published yet, we are still fighting with the referees and so on, but the point is that we are claiming that this robustness of the entanglement is pointing out for a topological structure, sorry, let me come back. A topological structure where we have a insulator, a bulk insulator, surrounded by superfluid edges with the highest possible entanglement within this thing, and that could be useful somehow for some applications. Right, just to mention the other parameters, all of them see some signature at that particular transition point within the density, for example, but they are smoother. So, for example, the average one, there is some non-monotonicity, but nothing more than that. The effective, the average only within the effective chain is the green one, is also showing something, but smooth. The average superconductor parameter also doesn't show much. And then when we consider the entanglement between halves, that is clearly pointed out here on that transition. That's just because at this critical point here, we already have an insulator in the bulk. So essentially, we are disrupting the two sides of the chain. So that's the natural signature that you have reached the insulator within there. Okay. Then we could construct a nice phase diagram where we have that metallic intermediate phase between a usual superfluid phase and these topologically structured systems. And with that, I thank you very much for your attention.
Thank you, Vivian, for the very nice talk. Questions for Vivian?
Well, if I'm not mistaken, when you show us the density as a function of the curvature of the, it was nonlinear.
Oops,
I had the
I'm
impression
going,
that
I'm going further. So this one, for example,
no,
it was density, right? So
yeah,
it's,
after that,
yes,
yeah,
yes.
confinement effect. So it seems that when you increase K, then you reach, when K is like the green line. Oh no, it's not. I mean, then it keeps on opening.
Yes, then it becomes broader and broader.
Yeah, but you are doing this right in the
Yes,
potential.
yes, that's the confinement
And
strength.
why it's widening the
The center region?
Yeah.
Well, that is actually happening from, for example, from the green to the pink curve.
Yeah.
Is that your question? If
Yeah.
I'm occupying
Yeah,
a broader...
You are confining more and more, right?
Yes, then I increase the effective length or where the particles lie, right? So was that wrong?
Yeah, yeah.
All right.
No. I'm just asking if how can I have a feeling of it?
All right. So actually, yeah, I think you just noticed this here. Oh no, that's just because. Okay. So it's not a different thing. So this effective length here is correct in this case because it's just considering where I do have particles. So if I confine at some center portion, then it becomes smaller. But then you are completely right that the plateau where I saw the fully occupied sites are becoming broader when we increase the K. Yes.
When you confine
but
more
we
and
didn't check if this increase is linear. That what you were.
No. I just was trying to have a feeling about that because it seems to me that you were confining and this is becoming broader. So I could not have a. But I thought it was no monotonic, but I was wrong, so it's okay.
Right.
And I have a second question. Can you give us a feeling, because I think it's interesting that you said that when the system is has less entanglement, you have more work being possibly extracted from that, as I could understand. Can I have a physical feeling or an example of, I don't know, perhaps a real system or even in the model? Why it would be that?
Yeah, I think that's a very good question, and I think I don't know the answer, because you see when we actually, okay, we are trying to attempt, let me just try to go back there, we are trying to give some information of how these two quantities are related, but actually if you think with all the process that we did in here. So it's not really a direct connection. So for example, with here, I just started with a ground state with the minimum entanglement. So, and while here, I really have, there's the dependence on the quench that is clearly very different. So it's not seems to be a direct connection that we could extract, right? Yeah, we are trying to, yeah.
I have a question myself. If I understood it correctly, you showed this very nice connection between entanglement and signatures of quantum critical points, right?
Right.
So that was one of the big lessons that we got here. And I was thinking about how do you measure this in experiments, and you showed later in the bonus that you had a way that you could calculate magnetic susceptibilities.
Yes.
In terms of entanglement.
Yes,
and you could do all this mapping. And how is the experimental scenario now? It's to actually measure these things, to actually...
Well, there are measures of magnetic susceptibility, and I think it's Marcus Greiner work, and also trying to connect with entanglement. It was a different type of entanglement, right? As I said in the beginning, you can define entanglement almost between everything within the system. So, but actually, for the single-site measurements, you need to do the tomography thing that I think is going out of range now at the moment. I think to really map, for example, to have some experimental points on that graphic that I showed to you. Yeah, I'm not sure if they are still interested on this particular stuff yet. But the idea here was more to try, because most of the time when we are trying to to see things via entanglement, people say, okay, you calculate the mathematical stuff there, and who cares? So the point was to try to see that it's not so far away from things that you could, in principle, measure. So I think we just have to keep going.
Optical lattices, I don't know, maybe else, I don't know.
Yeah, in optical lattices definitely would be the best setup for it. But
okay. More questions?
I have a short one. Can you also use the same tools to study off-diagonal disorder?
yeah, that's a very good question, and that's something we are trying to find out how. But I don't have an answer yet.
Thank you for the very nice talk. And you show a graphic for hexagonal and other two-dimensional lattices. Did you use the same approach or a similar approach?
No, that's a very different approach. That is work performed with the group of Teresa Paiva, and these are with Wilda Wani, her postdoc work, and there they do quantum Monte Carlo calculations. So I'm sorry for not stating that explicitly, but yeah, these are other methodology.
Thank you.
Okay, if there are no more questions, let's thank Vivian again. Before you go,